In this video, we're going to talk about the central limit theorem and its applications. So we're going to start with these two assumptions. So A, we know that the distribution of some population, we know its mean and its standard deviation. So those are two things we'll need. And then we're going to assume we're collecting all possible samples of some size from the population and finding all of their means. So, for example, let's say we took all samples of size 30, and then you found the mean of all of those samples. You could then make a new distribution. And that distribution will take on the shape of a normal distribution. You could also say bell curve there, if the population is bell-shaped or if the sample size is big enough. So if the original population has a normal distribution, then big enough, the sample size can just be size 1. It's already a normal distribution. If the original population does not have a normal distribution, then the sample size must be at least 30. So generally, the distribution of the means of all samples will be much narrower and steeper than the whole population. So if this was your normal distribution, if you take the means, if you average things out, your outliers kind of get averaged out, and so it becomes much narrower, the graph. So we can easily calculate the mean and the standard deviation of the sample means distribution. So this new distribution, the mean is going to be the exact same as the mean of the original. So the centers are going to be in the same spot. But as we talked about, the standard deviation is smaller. It's a thinner distribution. So the formula for the new standard deviation, you take the standard deviation you were given for the original population and divide it by the square root of n. So you would take the standard deviation you're given in the problem divided by the square root of how big of sample you're taking. Okay, so we're going to look at some application problems. So we can solve these just as we did the normal distribution problem. So we'll be able to use normal CDF after we found mu x and sigma x. So remember, mu x is just going to be mu, and sigma x is going to be the standard deviation over the square root of n. And we'll be able to put it in the calculator just like that. So number 1 says women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5. So part A says if one woman is randomly selected, what's the probability that her height is between 60 inches and 65 inches? So since this is just one woman being selected, this is just like we've done before. We're going to do normal CDF. So since we want between 60 and 65 inches, our lower bound 60, our upper bound 65, we're going to keep the same mean they give in the problem. And the standard deviation stays the same because we're just taking one woman. So here, to get to normal CDF, let me clear this out so you can watch. Okay, we're going to hit second and then the one that says distribution over it. Normal CDF is number 2 here. So our lower is 60. Our upper is 65. The mean was 63.6. And the standard deviation was 2.5. So the probability that that one woman was between those heights would be 0.6373. Now, the next part that you see is a little different. Says if 16 women are randomly selected, what's the probability that their mean height is between 60 and 65? So notice here, we're not picking one woman, we're picking 16. And we're taking their average. So that's our n, 16. So we're still going to do normal CDF. And since we still have the same range, the range is going to stay the same, 60 to 65. The mean stays the same. 63.6. But the standard deviation, remember, we do sigma divided by the square root of n. So we're going to put in 2.5 divided by the square root, our n was 16. So you can just put in 2.5 divided by the square root of 16. And so notice we're going to get a much larger probability for the same thing, but we get 0.9875. Okay, so we're going to look at another example. So it says a ski gondola carries skiers to the top of the mountain. Its maximum capacity is 12 people or 2,004 pounds. So if we divide the 2,004 by 12, we see that an 167 average weight for each passenger. Because men tend to weigh more than women, a worst case scenario would be 12 passengers who are all men. Men's have weights that are normally distributed with a mean of 172 and a standard deviation of 29. So part A says find the probability that the weight of one randomly selected man will be greater than 167 pounds. So since we're just doing one randomly selected man here, we don't have to change our standard deviation. We're going to do normal CDF. Since it says greater than 167, we're doing 167, technically up to infinity, but we'll use 1,000 for our calculator. The mean was 172, and the standard deviation was 29. So here our probability is 0.5684. So there's a almost a 57% chance, 56.84% chance that any one man would be bigger than 167 pounds. Okay, so part B says, find the probability that 12 randomly selected men will have a total weight of more than 2,004 pounds. That is, find the probability that the mean weight of these 12 men will be greater than 167. So this is where we need the central limit theorem, because we're picking more than one person. We're picking 12 people. So we're going to do normal CDF. So again, we want greater than 167. So we're going to do 167 up to 1,000. The mean's going to stay the same. So remember, for the standard deviation, we're going to do the standard deviation we were given divided by the square root of n. So we'll have 29 divided by the square root of 12. So 0.7248. So just over 72% chance that the average of all of those men is over 167. So which of these probabilities is more relevant? Well, in this case, part B is because we're choosing 12 men to get on this gondola. So knowing the probability that together their average weight would be over that would be more important. We're going to look at one more here. So it says a safety light designed so that the times between flashes are normally distributed with a mean of 4 seconds and a standard deviation of 0.7 seconds. So find the probability that an individual time is greater than 4.30. So since it's individual, we're just choosing one. We're going to do normal CDF. So it says greater than 4.30. So 4.30 up to 1,000. Then we put our mean, which was 4, and our standard deviation, which was 0.7. So here we find that the probability is 0.3341. So part B says find the probability that the mean for 50 randomly selected times is greater than 4.3. So we're choosing 50 people, or sorry, 50 lights. So we're going to do normal CDF. Remember, the only thing that changes is that standard deviation. So we're going to take 0.7 divided by the square root of 50. So here we get 0.0012. So it says, given the light is intended to help people see an obstruction, which result is more relevant for assessing the safety of the light? Well, here, since you wouldn't be using groups of light at the same time, we're just using one safety light kind of per person, the individual, part A, would be more relevant here in knowing the probability that that light is working in the correct manner.